that when nuclear package splits, then we can see the decrease of this coherence pattern. So we can see the increase of coherence and decrease of coherence. So this green part is the quantum mechanical result, and this pink line is for our CT-MQC method. And here, as you can see, in atom phase dynamics, there is no decoherence because we have overcoherence problem. And also we apply the CT-MQC method for realistic situations. And in this case, we use the CPMD program using this linear response TDFT calculation, and we see the photodissociation dynamics of oxygen molecule. So the results are like this way. So here we can see the dynamics, the ring opening of the oxygen molecules, and here we calculate the coherence pattern of these dynamics, and we compare the CT-MQC algorithm and the corrected phase switch surface hopping algorithm. Here we use the EDC for decoherence correction. So as you can see here, in our approach, we can see quite nice decoherence pattern here. Okay, so we have symmetric C1O and C2O dissociation, and we can see the later coherence pattern for CC dissociation. And however, in this corrected approach, the conventional decoherence-induced phase switch surface hopping dynamics coherence pattern is quite messy. And for more efficient calculation, we actually developed independent or auxiliary trajectory method, which is called decoherence-induced surface hopping based on the exact factorization. So actually, coupled trajectory algorithm requires the non-adabatic coupling vectors among all Born-Oppenheimer states. However, in surface hopping dynamics, actually this non-adabatic coupling matrix element can be enough. And also, we don't need to calculate the coupling between all states. We just need couplings between the states and the running state. So this is the benefit of surface hopping algorithm. And also, we have to calculate Born-Oppenheimer force for all electronic states. This one is also time-consuming part. And also, this Born-Oppenheimer calculation should be stable for all trajectories. So coupled trajectory algorithm is quite efficient, but less efficient than the conventional surface hopping algorithm. So in this sense, actually we developed the modified surface hopping algorithm based on the exact factorization, which is called the decoherence-induced surface hopping based on the exact factorization, DISH-XF. So in this algorithm, actually we use the same nuclear equation as this conventional surface hopping. And for electron equational motion, we have difference because we have the coherence term here. So the equation for the electron motion, we follow these equations. Here we use the decoherence term from the exact factorization. And here actually I want to emphasize that this term is not the ad hoc correction for this equation. We have actually used this entire equational motion for the electronic dynamics. So it's different from the other conventional decoherence correction, surface hopping dynamics. And regarding the hopping probability, we use the same equation as the conventional surface hopping dynamics. And importantly, to calculate this quantum momentum term for this decoherence term, we use the auxiliary trajectories. In other words, we put Gaussian wave package when population exchange occurs. So the flow of our mixed quantum classical approach is following. So from the nuclear trajectory, we calculate Born-Oppenheimer properties, and in DISH-XF algorithm, we actually determine the running state based on the hopping probability, and we have additional step to calculate the decoherence term. We calculate these phase vectors, and we calculate the quantum momentum from coupled or auxiliary trajectories. Okay, then we evaluate the nuclear force, and we calculate this time derivative of the coefficients, then we update. Okay, so this is the conventional procedure. So the only additional part is this one. We calculate the phase and quantum momentum here. That's it. So by using this DISH-XF algorithm, so we calculate various systems. So first we calculate the symmetry model. So for the single avoided crossing, and we can actually describe the coherence pattern correctly. Here the blue one is the quantum dynamics, and the red one is the DISH-XF algorithm. So as you can see in this figure, we can describe the electronic decoherence in space. Okay, so if the nuclear trajectory follows the upper state, then we have the upper state electronic state, and if nuclear trajectory follows the lower state, then the lower population is 1. And also we can calculate the realistic molecule, and also we can capture the coherence patterns. We have sharp coherence pattern between S2 and S1 state first, and later we have coherence pattern, the broad coherence pattern between S1 and S0 state for this excited state dynamics. And also we can calculate sodium iodide pump probe experiment, which actually contains multiple crossings. So here, nuclear wave packet oscillates in the upper state, and it meets actually the avoided crossing region multiple times. So in this case, actually, we can calculate correct population exchange for long-scale dynamics. And also we use the algorithm in combination with the ensemble density functional theory in collaboration with Dr. Michael Filatov. And we calculated the excited state dynamics of the protonated shift base. So we actually see the cis-trans isomerization, and we actually calculate the kinetics of this chemical reaction. And also we calculated the ring opening dynamics of the cyclohexadiene. And actually here we can capture the correct light time with our work compared to the quantum dynamics simulation here. And in addition, we applied our algorithm based on this SSR approach. That we calculated molecular rotary motors like this guy and this guy. And here we were able to design an efficient molecular rotary motor by using our algorithm. So now I want to introduce the PyUnix-MD, the Python-based universal excited state molecular dynamics program. So this PyUnix-MD program is the Python-based program suite for trajectory-based excited state molecular dynamics. And we have multiple features. We can actually handle the Born-Oppenheimer molecular dynamics, coupled trajectory mixed quantum classical algorithm as described previously, and RMFast, switchy surface hopping, and decoherence induced surface hopping based on the exact vectorization, and so on. Actually, we have many interfaces with many quantum chemistry programs, and actually this is not public yet, but will be public soon via GitHub, and expected date is the end of this year. So actually I would like to show you sample input file for this PyUnix-MD program. Here actually we first define the molecular configuration, and for example in this case we have model system, one-dimensional model system. So we have model particle here, and we have one-dimensional position and velocity. And then we construct the molecule class, and then we have interface with other quantum chemistry program. Here actually we use the homemade model calculation, and then we define our mixed quantum classical method. In this case we use the DISHXF method. Then we define the various parameters. Okay, then we just run the dynamics. Actually that's it. This is the simple input file for our PyUnix-MD program. Then as a result, we actually obtain the populations and coherence patterns and other important quantities. And there are many outputs from this dynamics as other excited state molecular dynamics programs. And actually I would like to introduce the developers of PyUnix-MD program, and mostly it is under development with these developers, my students. And we have other collaborators from Bremen, Professor Thomas Braunheim, and New York, Professor Nipa Maitra. So as a summary, we actually developed the excited state molecular dynamics algorithm beyond non-adiabatic coupling for the electronic decoherence phenomena. So this quantum decoherence or quantum coherence can be captured with quantum mechanical feature of nuclei, the quantum momentum. And so we developed the PyUnix-MD program, and it can handle the coupled trajectory with quantum classical dynamics, and DISHXF, which use the auxiliary trajectories to calculate the quantum momentum. So this one can handle the quantum coherence without any error correction actually. So this program will be released soon. We expect the time as the end of this year. And thank you for listening, and I will be happy with your comments and questions.
Thank you very much for Professor Min for a great talk. We can take one or two questions or comments. Yes, Sebastian, please go ahead and ask a question.
Well, thank you very much for this nice and very interesting talk. I have a question regarding the DISHXF method.
Okay.
So are you familiar with this augmented FSSH method of Joe Subotnick? That is also a method that uses auxiliary trajectories and difference gradients to calculate the coherence corrections. So can you say how similar these two methods are?
Well, actually, I'm not that familiar with this Joseph method. And well, actually, I would say that in our case,
I will just briefly explain our algorithm. And actually, when we have the non-adiabatic coupling, then we have population exchange, right? Then we just put one auxiliary trajectory for that specific state, and we put no other, Gaussians more than one for that population exchange. So this is, and the auxiliary trajectory follows the potential on the specific state. Then we actually approximately reconstruct the nuclear density from these trajectories. Then we calculate the quantum momentum. Then we calculate the coherence term. Actually, this is our algorithm.
Okay, good. Thank you.
Okay, any other questions or comments?
Yeah, I have a question. I have a little question, yeah.
Oh, Wenjun, please go ahead,
Okay.
yes.
Somewhere you said that your scheme is some beyond non-adiabatic dynamics. So what do you mean then? Why beyond non-adiabatic?
Actually, here beyond non-adiabatic dynamics is that this non-adiabatic coupling is actually, when you use this kind of AMFS or conventional surface swapping dynamics, the classical momentum is coupled to the non-adiabatic coupling vectors. That's what I mean by the non-adiabatic coupling. And actually, so this is conventional dynamics. Excited state molecular dynamics. Then based on this exact factorization, we can obtain the additional term with quantum momentum part, as I showed before. So this term actually was unknown so far. So I said this is beyond the conventional non-adiabatic coupling. Yeah.
Well, surface hopping is not the only approach to do this non-adiabatic dynamics. For example, you can think of the mapping model. So where you have this first order degree coupling, but it's exact. Exact in the sense that if you treat nuclei quantum mechanically, and then it is also exact. So, and if you treat nuclei classically, you still go beyond Alogrithms dynamics, and essentially parameter free. So I want to know why do you call non-adiabatic? Because non-adiabatic dynamics is everything already, right?
Actually, I forgot your question. What was the question?
Okay, my comment is that when you have more than one particular surface, like we call it non-adiabatic dynamics, right? So this non-adiabatic dynamic means everything, all effect. So in your case, it's just because exact factorization, just you get some additional term, right? But this, I agree with you, this is beyond the surface hopping, but not beyond the non-adiabatic dynamics.
Well, actually, in my talk, I was focused on kind of practical way to use this coupled equations. So actually, as a result, I will stick to the conventional way of this excited state molecular dynamics. But well, I actually discard many important terms actually, to be honest. But if we include this term, if you use this real exact coupled equations, then I believe it can go beyond the conventional trajectory-based method.
Okay, so I think I have to kick in, and for the sake of time, so maybe we can stop discussions here and then move on if there are no further questions. Okay, let's thank Professor Min once again for a great talk.